So I am really excited to welcome our next speaker, who you might have seen in the Unison Discord, helping people understand abilities, or one of the many functional programming communities where he helps people with distributed systems and concurrency and functional programming. This is Fabio Labella, here to present about distributed streaming on the cloud. Welcome, Fabio.
Great, thank you very much. Hello, everyone, and welcome to my talk on KLogs. So my name is Fabio Labella. I'm the Principal Distributed Systems Engineer at Unison Computing, which means I get to spend my days thinking about system design and then bringing them to life on Unison Cloud. So we have a very packed agenda for today because we're going to look into designing a streaming engine, and also we're going to introduce Unison Cloud and the features that we need to implement it, and we'll throw in, for good measure, some general techniques for designing distributed systems. So enter KLogs. KLogs is a streaming engine that's primarily designed for OLTP. So think about, state machines, user workflows, that sort of thing. And it's built entirely on Unison Cloud. But at the moment, it's still very experimental. It's a work in progress. So let's look at the API straight away. So the main type is this KLog type, which stands for keyed log. It's parameterized by a key and a value. And a KLog is an infinite sequence of key value pairs, which I'm going to call messages from now on. And the key semantic is that the values for a given key are in first in, first out order. But the values for different keys of a KLog are independent and unordered. So we have a per key order, and we can decide the amount of order versus concurrency by picking different keys. So the way we operate on KLogs is with this ability, the pipeline ability. It has 4 operations. Let's start with loop. So because KLogs have a per key order, loop transforms the values of a KLog on a per key basis. And it does so with this stateful sequential transformation. So you give it an initial state, which is again a per key initial state, and then a function that takes the whole state and a message and returns the new state and a bunch of messages that you're going to publish as the output. It could be 0, 1, or more. And each the values for a given key are processed sequentially, but different keys are being processed concurrently. Cool. So we have to have a way then to control the keys of a KLog, and that's what partition does. So you can see it transforms the keys of a KLog with this function, which takes a message, so a key value pair, and then returns the new key for that value. And it's a list there because you could filter out the record entirely by returning an empty list, or you could publish the same record with multiple keys if you return more than one. So that's partition. We then have merge, which interleaves the values from different KLogs, but just kind of publish them on the output as they arrive in order to produce this one output KLog. And finally, sync, which is for when we're done processing with our pipeline. So we want to run a side effect for each message. And don't worry about remote too much. For now, just think of it as a version of the IO ability that works on the cloud. So for side effects, and we'll see what remote does a bit more later on. Cool. So that's the ability. So the key idea is we're going to route messages to different keys and then process each key sequentially with state. But different keys are processed concurrently. So the messages for a single key are processed sequentially, but we have concurrency across keys. Okay, so we have our pipelines. What do we do with them? There's this other ability, and let's just have a look at the helpers that have slightly nicer types. So the KLogs ability for deploying and activating pipelines, basically. So we have a deploy function that takes a pipeline. Again, it's just a thunk in the pipeline ability, so a pipeline program. And deploys it to run on our KLogs cluster. And then a way of creating named KLogs. So pipeline, takes KLogs as input and outputs other KLogs. So you have to give you have to have a KLog to start from, and you can create one explicitly with named, and then lets you produce values to one of these named KLogs to start your pipeline. So you might be wondering where is this stuff running? Where's the cluster? But because KLogs is an ability, actually the handler is going to decide where pipelines are deployed. So it's good we can show examples without having to worry about where the cluster is and things like that. So let's look at an example. we are kind of having a word count example. So this Klog has a bunch of word count records. So the key is a word, and the value is the number of occurrences of that word in a given document. And kind of we have these records streaming in. But this Klog only has words that are uppercase. Then we have another word count Klog, same thing, word and frequency in a document, but this is lowercase, and we want to run a case insensitive word count. So let's write a pipeline to do that. We are going to merge upper and lower. So now we have one Klog that we can operate on. I'm going to call partition and take the key and just lowercase it. So now we're sort of joining, if you have a word that it's only different up to casing, it's going to go to the same key, which is the lowercase version of the word. And now that we have the right key partitioning, we can just do the per key processing with loop. So we have a count that starts at 0 for each key. And then we have this function takes the word, sort of the total, the old stage is the total and the current count for that word. We're going to get the new total and emit the new total. Assign new total to the state. So we are updating the state with the new total and also emitting the new total as the new value. So now we have words with the updated count, and we have the sync. And I'm not gonna show you like what print count JSON does, but it kind of just prints the count as JSON. So we can then deploy the pipeline, and then we'll see that as we produce a record to the upper Klog, it gets correctly outputted as like the lowercase version. Same thing with another record, and then if we have another record for the same key, we get the updated count. And similarly, again up to casing, right? So that is case insensitive. And same thing of another record here, and the count gets updated correctly, right? And that's it. That's KLogs. So to implement it, we have to have a look at Unison Cloud because it's got quite a bunch of unique features. So we're just going to mention three. Computations can move across nodes, and deployments are just code. So there isn't a separate like YAML-like infrastructure type thing. You just write Unison to deploy Unison. And also we have this typed transactional storage, which is integrated into the cloud. There's actually more, but I've got time constraints, so I'm just going to touch on what we need for this specific system. So let's start from remote. So the remote ability is sort of the main ability that you use when building cloud programs. And again, we can start by thinking of it as a version of I/O that works in the cloud. And so it's got a concurrency API. So you can sleep, you can spawn a thread and cancel it. You have a bit of an API for resource safety where you can delimit a scope and add finalizers to that scope that run if the scope fails or gets interrupted or whatnot. We then have an API for mutable variables, which are which you can write to atomically with this compare and swap operation. And then we have an API for blocking, where we create an empty promise, and then reading an empty promise will block until we write to it, which will unblock all the readers, and then we can create a new promise to wait for another condition, right? And those of you that kind of familiar with Scala will not be too surprised by this API. But the cool thing is that this API is not just a concurrency API, it's actually a distributed API. In particular, we have this concept of a location, and don't worry about the G for now, I'll get to that in a second. But location is a logical place on Unison Cloud. So it could be a different green thread or a different core, but also a different machine, a different data center, or a different region. So at the moment, we have a fairly bare bones API for locations. You can get the location that you're at the moment, and then ask for a location nearby, which is sort of a different core on the same machine, or a location far away, which is another machine. But this will expand as the cloud matures. And the main forking API, which is the Tacha, the more primitive one, actually takes a location. So we can fork to a specific location, which isn't just a local location. It could be another machine. And not only that, but like all the types that we looked at, like thread and ref and promise, they all carry their location ID. So as a result, the whole remote API actually works across nodes. And this is interesting because in addition to the normal concurrency patterns, like spin a bunch of threads to fetch some data, we can also implement things like scaling out just by forking to different machines. And also with ref and promise, we can build communication channels that replace explicit networking code. Now, obviously, the guarantees degrade accordingly. Like, for example, if you try to cancel a task on the same location you're at, that's always going to succeed. But if you try and cancel a task that's on a different machine and there's a network partition, you will not. But it's still nice. Like, the point of this API is not to like hide the difficulty of distributed computing, but to make sure that we can still tackle those problems with normal code at a high level without having to worry about, like having to encode logic into like a messaging protocol, even though we still have to deal with like distributed problems, as we will see. So final thing about remote and locations, location are actually typed with the effects they support. So that's what this G parameter stands for. And Unison Cloud offers this like default pool, the cloud pool, a pool of like a location that you can access. And these locations offer a default set of effects. That's basically the effects that the cloud can do for you. And this means that we can send to another program, we can send programs to another node safely without worrying that the node does not support an effect that we want to run. So in this case, I am logging to a distant node, and I know that I can log because the kind of type of the location tells me so. Okay, cool. So we have these remote programs. How do we interact with the cloud? And this is what the cloud ability is for. It's very big, so I'm just going to like do a very quick run through. You can get an environment for your code to run. And then if you want to run a single, like a one-off job on the cloud, you call submit, you pass the environment, sorry, and your remote program, and it kind of returns the result in this cloud ability. And cloud is an ability because we have different handlers. So with cloud run, it's actually going to go onto the cloud and kind of deploy your code and run it. Whereas Cloud Run Local is going to run a simulated version with in-machine concurrency on your machine, and you can use that for testing, for example. So complete example, literally complete example to submit some code on the cloud, you call cloud.run, and then you pass a program to it that calls submit to the default environment with your remote computation, and you're done. So this kind of covers one-off jobs, but what about long-running programs? And we have an API called daemons. It's also in the cloud ability. So named kind of creates this named placeholder for your daemon, and then you can call deploy with the daemon and the environment and sort of the code that you want to deploy to your daemon. And this again, it's a programming remote, and this void here just means that this is not meant to terminate. So it's generally an infinitely recursive thing that keeps running until you stop it. But what's a daemon? So a daemon is a serverless long-running process, and it's serverless in the sense that you don't control when the machine running it goes up or down. And so for it to work, Unison Cloud restarts your daemon whenever there's a change in the underlying infrastructure. So if machines are going down, or with sort of increasing the size of the location pool, that's kind of transparent. The daemon gets moved or restarted. But as a result, it means that there might be one or more instances of your daemon running at any given time, and therefore this is still a fairly low-level tool. We still have to do distributed system sort of trickery to make sure that this behaves correctly, but this is the like minimal building block that we need to run long-running code in a serverless environment. So the core idea is that we can implement all types of distributed systems by deploying a daemon that spawns remote threads. Kind of all topologies can be expressed with this. But there's one piece missing, which is storage. So we have this sort of typed key value store with support for multi-key and multi-table transactions. And transactions are also just Unison programs in a given ability. So there isn't like a separate query language. You just write Unison and it's kind of run transactionally and persistently. And because we have transaction and the storage is tight, we can build arbitrary data structures. So this is what the API looks like. We have a table type with key and value, and it's operated, surprise, surprise, with an ability, the transaction ability. Very simple. You can write, read, and delete from a table given like a key. And to run transaction, we have this transact function. And again, our transaction is just a program in the transaction and exception ability. We don't allow other effects in here because you can't roll back an arbitrary effect, but you can have arbitrary control flow in there. So again, just normal code. And this operates in the storage ability, which is supported by our cloud tool. So you don't have to do anything else. And you just have to pass a database to it, which is the unit of transactionality. So within the same database, you can do transaction among multiple tables, multiple keys, whatever you want. And you can create a database in the cloud ability as part of your deploy code. So let's have a look at an example. We're actually going to use this data structure for KLogs. So it's a pertinent example. I want to have this linear log data structure, which is an append-only log with a type parameter. So it's parameterized by the type of values we're going to put in there. And we bundle the database in it so that we don't have to pass it to every function. And then we have this index table. This is a table of unit, which means it's a single value. And this is tracking the size of the linear log which is also the first slot we can append to. And then we store the values in this other table that has like for a given index is going to give us the value. So it's similar to an array. Okay, let's look at the size function, and this is a function in the transaction ability so that we can compose it transactionally without transactional code. I said transactional a lot, but you get what I mean. Very simple. We just read the index, and if there's no value there, it means that the size is 0. This returns an optional, so get array else will be optional. And now let's look at how to append values to this linear log. So it takes the linear log and the value. And I wanted to show you an example with transact. So that's why you see this storage and exception ability here. So I call transact, and now this block is all running transactionally, so we don't have to worry about race conditions or anything like that. So I just get the first free index, which is the size of the log. I write at that index with the value that I'm provided, and then I increment the size of the linear log. And then final example, how to sort of query this linear log. Specifically, I want to query the linear log from a given index all the way to the end. And I've decided to return remote here, which is kind of a way of simplifying type signatures a little bit if you don't want to see kind of all the abilities. And the way I do it, I have this little helper run, which takes a transactional program, transacts it, and then uses this toRemote helper to convert all the effects, to embed them really in remote using the default pool. So once I have that, I can use it to compute the end of the linear log in its own transaction, and then get the range of values from the start that the user provided me to the end. And I'm going to use remote ParMap, which does single machine concurrency to fetch all these values concurrently. And I'm just going to read the values at the right index. And this is going to get them all concurrently, but return them in order. So we now have a list of options, returned by try read, and we call sums, and we're done. We have our list result. Cool. So quick recap, we have the remote ability for concurrent and distributed control flow, the cloud ability to do deploy with a function call. We have daemons, which are low-level, long-running processes, and then we can build durable data structures with transactions using the storage ability. So back to the task at hand, we have to implement KLogs. We have the KLog type, a couple of abilities, so we have to write handlers for those abilities, and then a distributed runner that can run this type of code. So let's start from the KLog type, and here I want to show you a little trick, because this type is used in an ability, and so different handlers might have different representation for this type, depending if it's a local handler, a simulation handler, or the actual production handler. So the way you can solve this problem, since Unison does not have abstract types, is just by saying, well, the KLog is just an ID, where the ID is this small amount of bytes, and then we can use this ID to index into arbitrary state. And so that's a very generic way of writing complex handlers. So how do we build these IDs? Well, we have two types of KLogs. We have the named ones, and in that case, we just we get the name, and we call this function. This is a hashing function, and we're gonna hash this little label n, which lets us know this is a named KLog with the name, and we have our ID, so a bit of wrapping. And then we have another type of KLog, which is in the pipeline ability, various operations, take some functions and some input KLogs and give you an output KLog. So within the handler for that ability, we're going to use the same strategy, call a hashing function, use a little label to say, okay, this is for partition, and then pass the arguments to that call to partition, so the function and the input KLog. And this is like a deterministic way to compute all the output KLogs of a pipeline program. Okay, so we have our basic index, but now we have to actually decide the storage shape that these KLogs are going to take. And bear in mind, our storage is going to have to host KLogs at different types. So we need to have a way to represent heterogeneous types. And this is like this built-in called any. It's a kind of like a low-level unsafe API, but these type parameters are going to keep us safe. But basically, you can put any type into an any, and then given an any, extract it at any type. But you have to make sure that it's the right type that the receiving code is expecting. So now that we have that, we could represent KLogs as like this table from a KLog ID to a linear log of keys and values. But this is actually not granular enough because it's too ordered. We said that the KLog is only ordered in a sequence per key, but there's no order among different keys. So instead, we're going to split each KLog into this loglet notion. So what we say is like, let's create this key type, which has the klog ID at a given key, user provided key. And then we have a table of loglets, which is a table from this key to a linear log of values. Right, so it looks like this. We have a bunch of linear logs, and you can see here we have the klog FTC at key 6, and this is like the values for key 6. And then here we have the same FTC klog, but at key 7. And so we represent all of it as these like little loglets, which are like per key portions of a klog. Okay, how do we consume one of these, right? And in general, how do we consume a linear log in this sort of streaming world? So we introduced the notion of an offset, which is the index of the last value we successfully processed. So if you want to build a consumer for a given loglet, we're going to have to read the last offset that we've seen, and I'll show you how this is stored in a second. Use the key to get the right loglet, and then use the from helper to get all the values in the loglet that we haven't seen before. Then do the processing, which is going to vary depending on what the pipeline is doing, and then advance the offset. Then we're going to sleep a bit, and we're going to recur again. And we use this polling strategy because it actually works across restarts. So even if we crash, we're going to go back up, poll, and we're just going to get any messages that we didn't read the last time. And also, thanks to offset, we achieve at least once processing because we only advance the offset after we successfully process the message. So even if we crash or there's an error, we're not going to lose any messages. We might process them twice, though, and we'll see how to fix that problem too later on. Okay, so the question is, how do we store the offsets? So this is the same example I shown you before, was like, that case-insensitive word count. But this time I've just sort of named the KLogs explicitly. And when you do that, you realize that this is sort of built a little computation graph where like you have computational stages, pipeline stages joined by these output KLogs. But we've also seen how these KLogs, how their ID is computed, right? So it's just a hash of the stage that produced them. So this is a very important point, which is like we can use the output klog to univocally identify the pipeline stage that produced it, right? So there's like this one-on-one correspondence between a pipeline stage and its output klog. But this is not quite the full picture because remember, if you look at the running stages, there isn't one running per klog, but there's one running per key of each klog, right? Because we want each key to be processed concurrently. So if we look at it again with the ID, there's like, okay, for the same klog ID, there's one running at key 1, then a key 2, and one at key 3. But we've seen what this is, right? This is the loglet. The loglet was exactly a portion of a klog at a given key. So in other words, there is a pipeline stage running per loglet. So quick recap, each pipeline stage maps one-to-one to an output klog ID, and one or more klog IDs are fed as input to a stage, but actually there's a stage running for each key of each input klog ID. So in other words, there is one running stage per loglet, and therefore we have to keep track of progress per loglet for each running stage. So how does this look in code? We have our loglets table. We're going to add another table, progress, where for each output klog ID, so for each stage and each input loglet, we keep the offset, right? And actually, we're going to add a little piece of state additionally, which is this, again, it's represented as any, and we need that because loop has to track this extra state. So merge, sync, and partition are stateless, but loop has to have this extra state, so we're going to track it in the same progress table where we track the offset. Okay, so we can imagine like a very naive implementation where we spawn a consumer per loglet, per stage, per pipeline. And actually this scales pretty well because the keys are unit of scaling, we spawn one consumer per key, and so this scales super well. But actually resource utilization is very poor. And to understand this, think about the consumer is spawning, right? And there's a consumer per key. But at any given point, there's only a small subset of key changing. So in other words, most polls are returning nothing. So we're wasting a lot of calls to storage to poll, whereas only a few keys will change at any given point in time. So this has bad resource utilization. So instead, we have to go with a slightly more sophisticated idea for our architecture, which is we're going to spawn a fixed number of workers. And whenever we write a record to a loglet, we're also going to write its key to one of a fixed number of logs, which I'm going to call notification shards. And then we're going to map each worker to a single log, so to a single notification shard. And it's called a notification shard because essentially when you read some keys from their log, it means, okay, those keys have changed. So I now have to go and do some processing. And that means that we have one pull per worker. So instead of having one pull per key, or which there could be millions, like the number of users, we have one pull per worker, and we can decide how to size our cluster for the optimal scale to resource utilization ratio. And then workers are going to host and invoke pipeline stages. So instead of pipeline stages kind of being recursive, they're going to get woken up by the worker when needed, and then they go back down to sleep. And therefore, a pipeline stage only runs if it has work to do. So again, let's have a look at a picture. This is our loglets table. And we also have this other bit of linear logs, which are our notification shards. There's a fixed number. And each notification shard has a bunch of keys. And a key being here means that something has just been written to the corresponding loglet. Then we have a worker per notification shard, one-to-one mapping. You can see it's color-coded. And the worker is going to pull and get the keys, and then given the key, it will know which pipeline stage to run. So again, color-coded, and then the pipeline stage is going to go to the relevant loglet and do its thing. Okay. So again, back to the code, we have to add more states. We're going to have this shard type. Again, it's going to be like a fixed number, so it's just a wrapper over a nat, which is a positive integer. And then a table with a single value, which is the shard count. Again, for now, imagine it's going to be constant. And then we have to create these notification logs. So a table from that shard to a linear log of keys. So we don't copy also the values, we just copy the key, because that's enough for us to know which loglet has changed. And then obviously we are processing these notification logs. So we need another table for the worker progress so that we know the offset of each worker. And remember, we use shard here because there's a one-to-one correspondence between a shard and a worker. Okay, so how do we produce to a KLog then? We have a KLog ID, a key, and a value. So first of all, we build a full key, which is the KLog ID plus the user provided key. And I'm going to show you the any wrapping for now, but just in this slide, then it's a bit noisy, so I'm gonna sort of skim over it. We then have a first transaction that gets the right loglet given the key and adds a value to that loglet. So we already had that. But now we also want to write to the notification shard. So we get the number of shards, hash the key, and then compute the target shard by doing the hash of the key modulo the number of shards. We can then get the right linear log from the shard table, the notification table, and add the key to our linear log. So notice we obviously notify only after the record is written to the loglet, because otherwise we kind of waste some time. If we tell the worker, hey, there's a key for you, and then there's none, it's a bit of a wasted round trip. And also we use this strategy of hashing and doing the modulo so that two changes to the same key will go to the same shard, which means that they will go to the same worker, which means then the worker can run it sequentially per key, which is one of our semantic requirements. Okay, so we said that the worker hosts pipeline stages. So how do we represent that? We have an in-memory map, and there's a stage running for each loglet of a KLog. So we say, well, for each KLog ID, the input KLog, we represent key stages with this function from key to side effects. And this is a list because you might have different pipelines that want to read the same input KLog, so it has to be a list. Then we have our worker. It's assigned a shard, and it's again like a polling recursive function. So kind of polling periodically. It's going to do the same dance, really gets the last offset from the worker progress table, gets the notification log that it's assigned to from the notification table, reads all the values that he hasn't seen. And then those values basically represents which keys have changed since last time we were operating. So for each of those keys, get me all the pipeline stages that are relevant and then run them all concurrently. And there's only a little detail that is crucial here, which is this call to distinct. And the reason you need this is remember, we run all these concurrently because we said, okay, multiple keys can, separate keys can run concurrently. But if we get a case where the same key gets written to twice, and then this batch contains the same key twice, and we don't call distinct, then we're going to run the processing for one key concurrently twice. So, which is going to break our sequential promise. So we do distinct, so we want the set of changed keys. Cool. So kind of that's the basic structure. So now we have to write this function, this handler really, that takes a pipeline computation and gives us this map. And we do this for each pipeline that is deployed and then merge the maps together to build that map of stages. And I don't have time to go into the detail of like how to write a handler, but basically it's a recursive function that peels off a step in the computation you're handling. I have some immutable state which is going to get updated with each layer of interpretation, and then I resume to keep going until I'm done. So it's basically an accumulator that we keep adding stages to, and once we're done, we got to the end of the pipeline code, we just return the map of stages, and we have a map of pipeline stages to feed to the worker. Cool. So actually, all the logic for KLogs proper is in here. We're going to start from sync, which is the simplest one to translate. So this is like the syntax for the handler. This F here is the user provided function. So first of all, we have to compute the output KLog with that hashing idea. We don't really publish to this KLog because it's a sync, but we still needed to identify the stage. Then the logic for a sync is very simple. We are given this function here. We just have to run it for each message. And so we are now to build a stage that will run for each loglet of this input KLog. So again, very similar idea. It's just not recursive. We get the progress, like the offset from the progress table, given our KLog and the key. So for a given stage and a given loglet, give me the last offset I've seen. This is a little helper to kind of save some code. Okay, now that I have the key, give me all the messages I haven't seen from the relevant loglet. For each message, I'm going to run my logic, which in this case is just running the side effect. Then I'm going to compute which offsets I've advanced to, update the progress table, and that's my stage. So once I've defined the stage, I'm just going to insert it into that map and keep interpreting. So now I successfully added a layer of interpretation of a pipeline. Partition, again, looks like a lot of code, but it's the exact same code. The only thing that changes is the logic. We are given this function from the user. We run it and returns a bunch of keys. And then for each key, we're going to publish to the output KLog the input value at whatever key the user decided. The rest is exactly the same. Merge, again, sort of tiny differences. We compute the hash a bit differently. In this case, we don't have a function. We just have a bunch of input KLogs, so we have to include them all in the hash. The logic is just to publish, because we'll just, as soon as we get values from any of the input KLogs, we just publish it onto the output KLog at the right loglet. And there's we manipulate the map slightly differently, because remember, this stage has to be woken up when any of the input KLogs writes a message. So we're going to insert it at, for any of the input KLogs that the users passed in, we insert the stage in for that KLog in the map. So when any of them gets a message, the relevant stage gets woken up. And then finally, loop. This is the hardest of them all, but still fairly reasonable. The logic runs the user provided function, given a state, a key, and a value, and we get the new state and a bunch of new values. We're going to publish all the new values to the output KLog at the right loglet and returned the new state. And stage is also a little bit different, because remember, in the case of loop, we had that extra any to keep track of in the progress table. So again, a little bit of helper code here to fetch both the last seen offset and the previous state, which we managed to commit, which could be the initial state if it's the first time this runs. And same thing here, when we update, we also update with the new state. And then the only other difference is, like, we cannot just do a for each, we have to do a fold left. So we thread the state through each of the messages. We kind of call the logic and thread the state through until we get the final state for that batch. And that's how we translate pipelines. But there is a little issue here, which is, the processing semantics. Because remember, stages are triggered by messages. Whenever there's a message to a loglet of a KLog, a stage gets triggered. But retriggering a stage can affect correctness. So if we have a stage that's doing a sum, like in our word count, and we sum the same record twice, because we receive it twice, then obviously that's not going to be correct. So we need to deliver messages exactly once. And the way we do it is we already have at least once processing, so we never lose messages. And we're going to add idempotent producing. So we're going to make sure that if you produce a message that's already been produced, it doesn't get produced again. So to do that, we're going to introduce an idempotency token and then kind of use transactions to check that token in the same transaction as when we write the message. But the kind of the difficulty here, we have to figure out a way of deterministically computing the item dependency token given the circumstances that produce the message. So in our case, though, we have all the data that we need. We can say, okay, we're going to store the output Klog ID. And remember, the output Klog ID uniquely identifies the logical stage that that is running at any given point. But there's like an instance of the logical stage running for each loglet. So we have to have the key, which will tell us which input loglet caused this message to be produced. And finally, we have to have the offsets onto that key, which will let us know at which point in logical time we have produced the message. So with this information, every time we are running a pipeline stage, we can compute the dependency token and then sort of like use it to avoid producing a message twice. So we have this message helper, that's the dependency token, the target key, and these are the values. And I have a list here because this is another little little tricky bit. Like things like partition or loop can return one output message. Sorry, can return multiple output messages given one input messages. And we have to make sure that that's considered as part of the same transaction for our dependency to work. We then have a table to store our dependency token, and now the kind of we sort of mostly done. All we have to say is that when we write to a loglet, we transactionally do a token check. So if the token check is not there, we write the token and publish to the loglet. If not, we do nothing. It's already been published, so we get our dependency. And the other thing to think to sort of the other neat part is that the write to the notification log is already idempotent, because even if we get told, hey, this key has changed twice and it's only changed once, it doesn't matter. We're going to waste a little bit of work, but the offset will save us from, we'll see that there's no new messages that we haven't seen. And so we don't have to do this check also for the notification write, only for the loglet write. So again, little reminder of how this works. We've seen all the code. Now, the picture should make more sense. We have a bunch of loglets. And also a fixed number of notification shards that contains keys to loglets which have been written to, fixed number of workers, worker pulls the notification shard, gets the keys, starts running the relevant pipeline stage, which goes to the loglet, then new batch, new set of pipeline stages, and so on and so forth. So that we sorted then the consumption side of the architecture, but the workers are also doing production, right? As part of the pipelines, we're like publishing new messages. So do we have a problem with that? So our write, remember, is like we write to two places. We write to the loglet, and then we write to the notification logs, to the notification shards. So the write to the loglet is actually fine, even though it's like you have a very messy assignment in the middle of this diagram. But if you think about it, there's exactly one pipeline stage running for a loglet. So each loglet gets written to by exactly one stage. There's no contention, no transactional conflicts. We're good to go. Okay, but what about the writes to the notification shards? Well, we have a problem here because, okay, on consumption, everything is fine. There's like one-to-one mapping. But on production, all the pipeline stages are kind of competing to write to the same notification logs. And so this is going to cause a bunch of transactional conflicts, retries, and it's going to slow the whole system down. So we can use the same idea then. We're going to say that each worker not only is assigned to consuming a given notification shard, but it's also assigned to producing. And so if another worker has to produce to this notification shard, it's just going to hop here. So we're going to use like this ref and promise to build communication channels. So then if I need to publish here, I'm going to send the record to this worker, which is going to batch it and send it over. And so we've eliminated the contention here because this is going to write things here sequentially with no conflicts. And we've solved this throughput problem. So how does this look like if you zoom in into a worker? So imagine you have this worker B and it's sending a record for a given key, and it hits the writer thread of our worker. And the writer thread is going to take the record and write it to the relevant loglet. You see, it's got the right key. And then take the key and add it to the notification shard. Now there's two things happening concurrently, so we don't know the order, which is on one hand, we can confirm to the initial worker that the message is safely stored. And on the other hand, the reader thread is purling from this notification log. It will get the key, wake up the relevant pipeline stage, and the pipeline stage is going to go to the loglet and fetch the new message. And I call this a safe part because even like two things are safe. First of all, we don't confirm the write until things are stored. And two, even if we confirm the write and then we crashed immediately after before we could consume this message, Because it is using polling, once we go back up, we'll still get it. So we never lose messages if we get an unlucky sequence of events. But actually, there is a nice fast part that we can use when we're not crashing, which is most of the time, which is after the writer thread has successfully written the message to storage, is now co-located with the entity that's going to consume the message. So we can just send it in memory on the same location, so same machine, and we still have to do the writes, but we avoid a bunch of reads from storage. So in practice, we only have to do this polling once when we start up. Then we go into this fast part where things go in memory, and if we crash, we're going to do one poll and then go back to this fast part. So saves a bunch of storage reads. So this is all fine and nice, but obviously this is all predicated on this very nice picture where all workers are aware of each other, there's no failures, and we know that this is definitely not the reality of a distributed system. So what do we do on a failure? So the first thing I want to do is, I don't want to mess up with the logic of the work. I want to abstract that away. So I'm going to have this pattern where we have a daemon, which is our starting point, which is going to act as a supervisor. And then the daemon is going to use detach at to different machines to spin out the workers. So we decouple like all the tricky logic of the control plane that has to deal with error handling from the workers. Then the workers are going to periodically send a message to this daemon, which we're going to call the heartbeat. And this is used for failure detection. So if there's like a deterministic failure, like the worker is like decided it needs to shut down, the heartbeat will contain enough information for the supervisor to know. But also the supervisor daemon can detect errors by the absence of a heartbeat. You know, this has to happen periodically. If I'm not getting one, there's an issue. I need to act on it. And the way we are going to represent this issue, or rather, the way we're going to represent all the issues that can happen, instead of thinking of like chaotic errors happen at chaotic times, is we're going to take a logical view of time where there's a period of time where everything is fine and we have a consistent view of all the workers. Then we detect a failure, and this is a sort of point of chaos. And then another point, and then another view starts, which is also consistent. And we're going to assign to each view this epoch, which is kind of logical time that increases monotonically. So yeah, the idea is like, you know, time moves in logical steps, which are called epochs, and in each step there's a consistent view, and in between there's this like a view change, which is where we detect a failure. We can represent this in code. So again, we have the, yet another monotonically increasing NAT. This time we called it an epoch. And we have a table with a single value which represents the current epoch. And this is going to advance as we see failures. And then we have a table for views, which maps a given epoch to this sort of view of our worker fleet. And there's a sort of bunch of data in there. For example, I have a map from the worker ID to a thread. This is going to be used by the supervisor to stop workers. We have a map from shard to their communication channel. This is used for like that communication between workers when doing when producing messages. And then we have this ref, which is stored by the supervisor, where the workers hop in to populate their heartbeats map. Okay. So the key idea is that we always spawn workers as part of a view. And then when there's a failure, we trigger a view change where we kill the workers in that view. And then the nice consequence of this is that a worker, from the point of view of a worker, they're always seeing a consistent view. They get spawned as part of a consistent view, and then if there's a problem, there's a new view with new workers. So the worker never has to directly be concerned with the specific error condition. So the way this looks like, again, we have this supervisor daemon, and it's going to use detacher to spin a bunch of workers. I'm not showing like all the arrows, but it's doing it for each of the workers. There's a little setup component in the worker code. Then a few messages get exchanged to finalize the protocol, and at some point the supervisor daemon is going to say, okay, now all workers are safe to activate. You are running as part of this epoch. This is the view that you're part of with all the details that you need to do your job. So at this point, the reader and writer start doing their thing. But there's another thread, the monitor thread in the worker, which is periodically hard beating to the supervisor daemon for failure detection. And it's also periodically checking on the epoch, because it's like, okay, I know I'm running at epoch n. If I see that now we are epoch n+1, I'm going to have to shut myself down. There's a view change. I'm no longer active. So this view change protocol is how we deal with errors in practice. And when the supervisor notices an error, is going to increment the epoch, and we see that eventually, like the workers are going to notice that and shut down. And the idea is that we want to seal the previous view, so shut down every activity in the previous view before we start a new one. So we make sure there's never like an overlap where the same key is being processed by two workers at different view, like in different epochs. So this sealing is really important. And we saw this sort of like slow path where the worker pulls the epoch in storage, but actually there's a fast path where the supervisor is just going to use remote thread interruption. And if there's no network partition, there's going to very quickly terminate everything. So again, this is like a common pattern that we can do with remote, where we have a more traditional path that is always safe. And then we have a fast path with this sort of concurrency. And that's what I meant when I said, even with reduced guarantees, this is still a useful thing that we can do both things in the same type of code without there, being very different layers like networking layer and like business logic layer. The other thing that's important is that views don't change in place. So there isn't like a single view object that mutates in place, but rather we have that table where each epoch had its own immutable view. And the reason we do that is that we have to be able to resume view change upon failure. So this is like, the diabolical part of distributed systems. Like think about the supervisor itself failing right in the middle of a view change. Now we need the new supervisor to come in and have all the information to resume the protocol. Otherwise, we get stuck in deadlock, basically, where we sort of halfway through killing the workers and we don't spin the new ones, for example. There's a bunch of tricky details that I don't have time to get into, but hopefully you get the idea that we can use view change as a way of dealing with all types of error, and then workers only have to deal with heart beating and checking the epoch. So we're almost there, but we still have another problem. As I said at the start, so in this slide I was describing the daemon supervisor as a single thing, but as I said, that we have no guarantee that there's a single daemon, right? Because the underlying machinery in Unison Cloud might be going through a deploy or increasing the pool of nodes and whatnot. So we might have two daemons running at the same time. One is just failed, one is partitioned away. So which one is going to be the supervisor? And we're going to introduce another idea, which is the idea of a lease. Again, a little piece of state. I'm going to tell you what these are for. But the thing about a lease, it's a mechanism for both leader election and failure detection. Again, we cannot use a supervisor for failure detection because we are the supervisor. So this is a different way of doing it. And also it's going to provide us with leader election, which we need to run that view change protocol safely. So the idea is each of the candidate supervisors, so each of the daemon instances running, is going to race and try and grab the leader lease by writing their own supervisor ID in it. So once you have the lease, it's valid for this duration t. And if you lost the race and you don't have the lease, then you will go to sleep for duration t and then try to steal it. So that means that for a period of duration t, the leader is in mutual exclusion. Well, there's a little bit of a caveat that I'll tell you in a second, but it's in mutual exclusion because you have the lease and you know that for a certain period of time, everyone else is just going to wait that time and is not going to try to interfere with your activity. And then every t, the leader can decide to renew its lease by incrementing this term, again, yet another monotonically increasing NAT. And that's how we get leader election. But the cool part is that we also get failure detection, because imagine I am the leader, I get the lease, and then in the middle of my leadership period, I crash. Now, the other instances that lost the race after T are going to try and get the lease for themselves, and they got to see, okay, I've already seen this supervisor ID, but they haven't incremented that term, so that means they're gone. Let me take over. And this is how we get both leader election and failure detection, which is cool. So what are the pros and cons of leases? Well, they are quite powerful given how simple they are. And it's actually, even though it might seem like it's based on time, we actually aren't agreeing on a global war clock time. We're not saying, hey, at 3 o'clock, let's all agree that that's the time when leadership changes. We're only measuring local time, which is much less prone to clock skew. But you can still be unlucky. This is the distributed system, so having poor luck is the norm. And what can happen is, say I am the leader. I got my lease for like 5 minutes. If I get super unlucky and I get a 6-minute garbage collection pause, very rare, but can happen. But then I'm going to wake up thinking no time at all has passed. I'm going to try and do something in mutual exclusion, but I'm no longer the leader, and that can mess things up. So you currently solve this problem for general set effects, but we're not running general set effects. We're running a rebalance protocol and monitoring. And so we do have one last trick up our sleeve, which is the idea of a fence. And the idea is this, like, even though I'm in mutual exclusion, okay, most operations I'm going to trust the mutual exclusion. But a very critical point when I'm doing some transactions, in our case, it's going to be like that, incrementing the epoch. That's a very critical thing where you have to do it once or the whole protocol sort of gets messed up. As part of that transaction, in the same transaction, I'm going to include a check on the lease. So I'm going to double check as part of the same transaction, am I still the leader? And this sort of a little piece of information is called a fencing token. And it's called fencing token because it fences off old leaders. So if I think I have the lease, I don't anymore. So I try and do this transaction and then the transactional check fails and then I'm sort of fenced off. I realize, hey, I actually no longer am the leader. Let me go back to watch the actual leader as opposed to trying to violate mutual exclusion. And that's it. So there's actually a lot more so that I don't have time to cover, like how to send pipelines to workers. Even shutting the system completely down is challenging because it's designed for high availability. So it's going to try and restart and sort of keep itself alive. But hopefully I kind of gave you a glance into sort of what goes on in a day in the life of a distributed systems engineer. So we started from a very nice, very simple functional API, but then as you could see, there's a lot going into making it work with resilience and scale. So conclusion, well, distributed systems are hard, we already knew that, but with Unison Cloud, you're only focusing on the parts that matter. So the abstractions of Unison Cloud aren't about pretending that these issues don't exist, but just because they exist, it doesn't mean that we have to code them in a very low level way. We still have to think very hard, but then we get to code them with the same nice tools that we have when we're coding less difficult code. So cool. So that was all. Thank you very much. I am System FW if you want on the user Discord. Always available to chat about whatever you want. And this is my blog where the slides are going to appear at some point. And I managed to finish on time, which I'm quite excited about because I didn't think it was going to happen. And yeah, thank you for your time.